Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet, and in this we were doing stacks topic, and today we'll start the new pattern which is stack based design. In this pattern we will learn how company asks design based questions where you have to implement few things, means different data structures using stack and vice versa. So let's see the problem. The problem name is implement queue using stack. And you know the functionality of queue. Basically you have to push, pop, peek and empty, and you have to design the data structure using stack such that it will behave like queue. And these type of questions are design or implementation based questions. So let's try to understand a problem with a given example. Suppose you have to insert 1, 2, 3, 4, okay, and the functions you have like push, 2 times push, then pop, then push and so on. So you know, as the question says you have to implement, means design queue using stack. So for sure you will use stack data structure. Now the very first operation is you have to push 1. So for sure you will push 1 here, then push 2. Now the third operation is to pop, and if you will use the same stack to pop, you will get the top element. And if you don't know how queue behaves, it behaves in FIFO structure, means first in first out. Suppose you have inserted numbers like 1, 2, 3, 4, at last you have inserted 4, right? So if it's stack, for sure when you will pop you will get 4, but if it's queue, when you will pop you will get 1, okay? So whatever has been inserted first, that will come out first as well. So it means if you will use a single stack, you won't be able to do it. Why? Because 2 has been inserted at last, and for sure if you have to make it like this, it should behave like queue. So when you will do pop, for sure first should come out. But how first should come out? If you want to bring first, you have to store 2 somewhere, correct? Means you need extra data structure. So hence you have to design the queue, but you have to use 2 stacks instead of 1 stack. The reason I already showed you, because you have to pop all top elements to return this innermost element, correct? Okay, so means we need one more stack here. Let's call it stack 2, and this was stack 1, okay? So can I say, like, I want to push and pop from the same stack 1, but I want my elements arranged in reverse order always. So the rule is very simple. Whenever you are getting any call function, means push function, suppose you have to push 1 here, definitely you will insert. But when 2 comes to insert, means when another function calls push to insert 2, before inserting 2 now, whatever is there in the stack, you will pop it out and you will push it in stack 2. Means you can assume stack 2 as a container, ki hey, save my elements, I'll take it later. Now 2 is the top element, correct? So that's what we will insert at the end of the stack 1, okay? And now whatever you have inserted in stack 2, means you have given the container to hold. Now you can pop it back and you can insert it here. So now can I say the stack has been designed in reversed order, and now if pop operation comes, for sure you can pop 1, because now what's the stack behavior? It will always pop the top element, and queue expected 1. Why? Because 1 has been inserted first, so hence you can simply pop 1 from here, okay? Yes, okay, after pop, let's call 2 push functions. So definitely you will pop 1. Now suppose you want to push 3. So what was the rule? Whatever has been, like whatever is coming now, it should go till the end, correct? So if you want to insert in the end of the stack, whatever is there in the stack, you have to remove it and put it in another container. That's what is stack 2. So whenever any push function comes, we will insert this. So can I write the function like this, ki in the push function, whenever it's being called, so we will check, and whatever is there in the stack 1. So while our stack 1 is not empty, okay? So whatever elements are there in the stack 1, we will simply put in the stack 2. So stack 2 dot push, what? Stack 1 dot pop, can I say? So when I will run this while loop, I will end up popping every elements and pushing in the container which is stack 2. And now in the stack 1, whatever element you wanted to push, let's say x element, you can insert this x in the stack 1. Means suppose 3 wants to come, so 3 can settle here till at the ending position, right? So now what we will do, now as 3 has been inserted, so whatever is there in the stack 2, we will bring it here, and now it will arrange like this in the reversed order. Means whatever were inserted at the first, now it appears at the beginning. So after this again we have to run a while loop. While our stack 2 is not empty, what we will do, now we will bring it back. So in stack 1 we will push after popping from stack 2, correct? Very simple. Okay, so means whenever there is any like push functionality, we will pop every such elements from the stack 1, we will push in the stack 2. Now we will push the element which we wanted to insert at the end, and then whatever was there in the container will bring it back, correct? Okay, so now can I say 2 will come here? Yes. Now when I have to call the pop function, what do you think? We should pop from stack 2 or we should pop from stack 1? Definitely stack 1. So we will simply do stack 1 dot pop. Now suppose we have to peek, means we have to just check what's the top element. Definitely stack 1 dot peek. Now if we have to check if our queue is empty or not, so we have to check the empty characteristic of stack 2 or stack 1. When can I say my queue is empty? Can I say when my stack 1 is empty? Yes, not because of stack 2. Because stack 2 we only used as a container purpose now to reverse our elements. When our stack 1 is empty, then only we can say yes, our queue is empty, right? So basically we are designing a queue data structure but using 2 different stacks, in which one stack we are using for push, pop and every operations, and another stack we are just using to reverse our numbers as a container. So I hope this much is clear. So let's write the code for this. First we will define our stack here of type integer st1. Similarly we will do for st2. Like basically we are declaring at class level, and once done, now we will initialize here st1 is equal to new stack. Similarly for st2 is equal to new stack. Once done, inside the push function, what was our task? Before pushing any element, whatever elements are there in the stack 1, pop and push it in stack 2. So what we'll do, while our stack 1, st1 is not empty, correct, we will push in st2, st2 dot push what? st1 dot pop, correct? Very simple. Now after that in the st1 we will put the element which we wanted to push, and after that again whatever is there in the st2, correct? So while our st2 is not empty, we will pop and push in the st1. So st1 dot push what? st2 dot pop, correct? Now reversed. Yes. So now in the pop function we have we simply have to return st1 dot pop, correct? Top element, because it's already been reversed now. In peek we have to simply read, correct? So return st1 dot peek top element, it's as it is. And now if you have to check is empty, as discussed, we have to check if the stack 1 is empty, then we can say yes, our queue is also empty, correct? So now we can run this code. Sorry, my bad, spelling wrong. Okay. Now as you can see it's passing, so we can try to submit also. And talking about the time complexity, definitely for pop, peek and is empty check, we are actually taking O of 1 time complexity. But for push, if you check, if you see here now, for every push, like when you are trying to insert something, you are running, you're popping every element from the stack 1, pushing in the stack 2, then inserting the element, new element in the bottom of the stack 1, and then again reverting the whole process from stack 2 to stack 1, correct? So we can say for push we are taking O of n time complexity. For sure it's fast, but O of n it's taking. Can we optimize it further? Means can we make in O of 1 constant? Let's see. So definitely we can do, but the only thing is here if you see, for every insert we were reverting our all elements from stack 1 to stack 2, right? For every push. And now we can optimize us further, like slightly better. Suppose you have to insert 1, 2, 3 continuously, okay? So there was no requirement for pop, but if you use the previous code, definitely for when you try to insert 1, okay, you will insert simply. When you will try to insert 2, you will push pop stack 1 from stack 1, you will push it here, then you will insert 2 here, then 1 will come here back again, correct? Again it will become 1, 2. Now when you want to push 3, you will pop 1, 2 will come here, then you will insert 3 here, then 2 and then 1. This is how you were maintaining, correct? Yes. But now the idea is that when you are inserting, don't change it until the pop requires, okay? So now push, push, push. Suppose now pop comes, like when you now you have to pop. So definitely which element you want? This. So the idea is pop every element from here and push it here, correct? And now instead of earlier what you were doing, pushing and popping everything you were doing from stack 1. Here push you will do in stack 1, but pop you will do from stack 2, because now in the stack 2 you have everything in the reversed order. So definitely you can pop 1. Can I say? Yes. So now you can give 1. Okay. So can I say I will erase everything from here? Correct. So 1 has been popped out. Now suppose push 4. Push 4. So definitely push you will insert. Now suddenly pop comes. Okay. Do you think you need to put it here, because then the 4 will become the topper element? I don't want that. Like as per the queue, 2 should popped out, correct? So now here's the rule. In push, you are not reversing anything, so O of 1, almost. Whenever there is any pop condition comes, correct? It's not like every time you are reverting and putting it here, no. In first case, you reversed, right? 1, 2, 3, 1 you popped. Again you will check, is my stack 2 empty? Correct? It's not. So means topper element is already there. Don't change, don't bring this 4 here. It's not needed. We'll pop 2. Again suppose 4 comes. Anyhow, third should be returned, right? Stack 2 is empty, no. Return this 3. Now stack 2 is empty. Now pop comes. Definitely 4 should be popped out. So now you will bring this 4 here in the stack 2, and now you will pop here. So the thing is, when you are trying to push, simply blindly you can push in stack 1. Okay. Now whenever pop comes, you will check if my stack 2 is empty, then only bring everything from stack 1 to stack 2 and reverse it. Correct? And then pop will always we will do from stack 2. Simple rule. Now you will say ki, like it's far better approach, right? Isn't it? Because push is O of 1. Correct? Now for pop and peak, what we are doing is कि whenever stack 2 is empty, then only we are actually popping every element and pushing it here, correct? Means nearly O of n, but very rare. Why? Because in every push case we were doing that, correct? And the pop will always be equal to push or less than push, correct? So number of push operations will always be greater than number of pop operations. So we should try to optimize the push, right? So hence we tried optimizing push, and now for pop and peak, the only thing we are doing is we are not reversing at every step. No, we are reversing only when stack 2 is empty. Means suppose like 1 to 100 you have to push. According to the previous one, you are taking 100 times, correct? Means O of n for every push, correct? But here suppose 100 times push and a single time pop, or suppose 5 or 6 times pop, correct? So when 100 times you popped, only 1 time you will take to reverse everything here in the stack 2, correct? And for next 100 pop, you are not going to again reverse it, because every time you will simply give from stack 2. Am I clear? Yes. So hence it's far better approach, and this is called amortized solution. And if you are going to tell this in interview, means from brute force to optimized one, how you will try to focus in reducing the O of n time complexity instead of push to pop, that is actually going to add value. So let's try to code for this. Here I have written the code for you. First you will make stack 1 and stack 2. When we are trying to push, you simply push in the stack 1. Whenever there is any pop or peak operation, remember, correct? Pop or peak, because in both the cases you have to check for the top elements, correct? So now what you will do for pop, first you will check if your stack 2 is empty, then only you will bring every element from stack 1 and push in stack 2. Otherwise, if your stack 2 is not empty, you can simply you can simply read the very top value from the stack, means O of one time complexity. Same you will do for peak, but instead of returning top element, you will simply peek it, means you will check it. And now the empty case, as you know, few of your elements might lie in ST1 also and in ST2 also, correct? So until or unless both are empty, you cannot say your queue is empty, because it might happen ki you pushed for 100 times and then pop comes, correct? Means all of your elements are there in stack 2. So you cannot say ki stack 1 is empty means queue is empty, correct? Simply if you have all 100 push operations and no pop operations, so you have the elements in stack 1, so you cannot say na ki ST2 is empty means queue is empty, correct? So hence, if both are empty, then only you can say ki yes, your queue is empty. That is why we have checked the empty condition for both the cases, okay? So now let's try to run as again saying, like both are optimized only, but if we still want to compare in both the solutions, this solution is far better compared to the previous one. So this was your Java code, and here is your Python code if you guys are from Python background, and here is your C++ code if you are from C++ background. And if you understood the reason behind why we have used two stack and how the amortized solution is far better than the previous one, then definitely you are eligible to go in the sheet and mark the very first question as done. And guys, if you understood, then do let me know in the comment section, and please try to write the code on your own and submit it on your own. Trust me, there are multiple companies which ask such design type of questions. You know, they might ask you ki implement hash map, implement queue using stack, and vice versa, implement linked list, implement tree data structure, and so on, and that is very important. So hence I am making videos for you all. And if you guys are new to this channel, you can follow the sheet. I'll add the links in the description. And please do like the video if you understood and if you felt somehow this video was helpful. And please don't forget to subscribe the channel as well. And that's it for this video. Let's meet in another video with some more interesting questions and topics. So then keep learning, take care of yourself and your family.